Alright guys, so we're going to look at one more thing hopefully before we go back, I believe. I really hope we're going to be back in person soon. So when we look at this here today, we're talking about triangle similarity, right triangle similarity. And we have right triangle similarity theorem. Now, if the altitude is drawn to the hypotenuse of a right triangle, then two triangles will form similar to the original triangle and to each other. So similar means that they are the same. It's just that one is bigger or smaller. We're changing the side lengths proportionally to each other. So all we did is we took a triangle, so this one here, and we made it a little bit bigger and a little bit bigger. So we're just increasing the size or decreasing the size, and that's it. So we're scaling it. We're making it bigger or smaller. We're dilating it. We're just making it bigger or smaller. So they're similar to each other. Now they're not the exact same, but they are similar. That means the side lengths are all going to increase by the same size or same amount or decrease by the same amount. And when we talk about similar, we use this one little line here. So this one little squiggle line means similar to each other. So when we look at these here, they're all similar to each other, and we can really look at the right angles to see how they match up. So let's take an example of this here. So this here is our first one, and we want to identify the similar triangles in the diagram. So when we look at this figure, it might be easier because it's a little bit hard to see, especially if you're not used to looking at these kind of shapes. So what we can do, and what I'm going to do, is I'm going to rebuild the three triangles. So this here is one of the triangles. I'm going to grab it here. So here's one of our triangles. And we have U. Boom. Well, I went on and paused the video and recreated these triangles for us. So when we look at this one triangle here, we have the big triangle, STR, this one here, where at angle T is our right angle. Then we had another triangle here at TUR, this one here, where angle U is our right angle. And it doesn't directly say this, or it says it, but it doesn't directly show it in the picture. But this here would be a right angle because we know that any two angles that make a straight line add up to be 180. So this angle here is our right angle. And we do know that these two sides are shared. So UT is going to be the same as UT. So that's kind of nice to know. But these here are our three similar triangles. And the way that I would look at it to find the similarity is setting them up so that the right angles are all in the same place. So here they're all in the bottom left of the triangle. So we can kind of see how they look. And now we just need to write our similarity statement. Okay, so I tried to pull up the special characters to see if I could use the triangle symbol, if they had a triangle symbol for me, but apparently they do not. So that's unfortunate. But we can go on and write our similarity statements anyways. Now the first one we can look at is the big triangle, STR. So we can call this STR. Now we will have a similarity symbol, which I can call up. That's not similar. Apparently they don't. That is really unfortunate. I'll have to draw it in here for us. It is similar. So we did our first triangle, STR. Well, the next triangle would be TUR. And this is going to be similar to SUT. and we have this here. Now, even though the TU and UT are congruent to each other, we're not going to put them in the same order because they're not, because they are congruent, but we're talking about similar. And we're talking about similarity, we're talking about the sides that are similar to each other, not congruent. So ST, TU, and SU are all going to be congruent, or not congruent, similar. SR, TR, and ST are all going to be similar because they're all the hypotenuse for each one of these triangles. And lastly, TR, UR, and UT are going to be similar. So we're talking about which sides are similar. So I went STR, so I'm going to go TUR and SUT because those are all the similar setups for this here. Now let's look at another one. Okay, so here's the next one we're going to look at, and we want to identify the similar triangles in the diagram. So again, what's going to be helpful is if we have three triangles to kind of look at and compare this to. And again, I set them up this way so that the right angles are all in the same spot, so that our right angles, let's have a pen, are all going to be right here. So we look at the big triangle here, MQP. MQP. So this would be our big triangle. Now the middle triangle is going to be this one here because it kind of looks like it's like at the middle size. So we have QNP. QNP. And our small one here, again, it doesn't say it, but this would be our right angle. And I'm going to name this one MNQ. And the way that we orient that one is, since this is the right angle, I'm going to put it in the corner, so that would be N. And our hypotenuse is this line over here. Okay, so we have our three triangles, and this is the makeup of this here. And now we need to kind of look at how they are similar. Well, we know that the side opposite the right angle, these sides here, are all going to be congruent to each other. Not congruent, sorry. They're going to be similar to each other because these are all similar triangles. Now it's going to work out that these sides here are going to be similar to each other as well, and it means that this other side are also going to be similar to each other. And these sides are going to be similar in this way here, which means it's going to be pretty easy, or kind of it's going to be helpful from there to just be able to name it. Now the way we name the first one isn't really important, so I can say MQP. MQP is going to be similar. So I started with the blue and then went yellow. So we're going to start blue, yellow, which is going to be QNP. And lastly is going to be MNQ. Then back out. So these are going to be similar to each other. And they're all triangles. I didn't have that on the first one. But if we were writing this out, it would be triangle MQP is similar to triangle QNP is similar to triangle MNQ. And that's all we'd have to do for this here. Okay. Now the last thing we're going to talk about today, because there's a lot more that we can talk about in chapter 9.3, and especially solving for side lengths of triangles, these similar triangles. But we're going to look at geometric mean, and we'll see if we have time to get back to the rest of chapter 9.3. But these are the only two things we'll focus on today. Now the geometric mean of two positive numbers, a and b, is the positive number x. That satisfies a over x is equal to x over b, so x squared is equal to ab, and x is equal to the square root of ab. Now all of this here, really we can just focus on this last part here. That x is equal to the square root of ab. And we can just solve for this here, which makes it a little bit easier. So if we have a geometric mean, our variable x, the geometric mean of these two positive numbers, is the square root of a times b. And that's it. So we could talk about them as fractions if we wanted. We can say that 24 over x is equal to x over 48. And we can go through the whole process, but really, the main thing is that x is equal to the square root of ab. Because if we went through and solved this, well, we can multiply both sides by 48x. 48 times x. 48 times x. And if we did that, well, here when we multiply both sides by 48, the 48 and 48 would cancel. And here the x and x would cancel. And what that would give us is 24 times 48 is equal to x times x. Which would just tell us that x squared is equal to 24 times 48. And to simplify, we would take the square root of both sides, telling us that x is equal to the square root of 24 times 48. But isn't that what we had at the beginning? Because again, our formula is this here. X is equal to the square root of AB. Our values of A and B are 24 and 48. So x is equal to the square root of 24 times 48. Now at this point here, we would need to simplify. So square root of 24 times 48, we can type this into a calculator. And if we type it into the calculator, we would get 24 square root of 2 is what we would get for this here. Now let's look at how we can type it into a calculator. Okay, so I'm over here on Wolfram Alpha. So this here is an online program that you can use to calculate these answers. And the way we would type these in is that we can type it in as parentheses, parentheses, 24 times 48. So I can type it as this here. So this is telling it that 24 times 48. And I put it with these extra parentheses because what we're going to do is take it to the 0.5. Enter. Does the 0.5 power? Because when I take it to the 0.5 or we put it to the 0.5 or 1/2, it's the same as taking the square root. Square root of 24 times 48. That's what we wanted. Now the exact result it gave me right here, 24 square root of 2. So this here is one way that you can go on and calculate the answer out. And that's how we can see that this here is the answer. So if it doesn't have whole numbers, if we have radical answers, we still have square roots left, we'll need the square root, especially for the homework. Let's look at another one. Find the geometric mean of 8 and 10. So we could go through the same process and do 8 over x is equal to x over 10. Or, because of the theorem that we have, we know that x is equal to 8 times 10, the square root of 8 times 10, the square root of a times b. And at this point here, so we just need to take the square root of 8 times 10. Well, for us here, 8 times 10 will be 80. So we're taking the square root of 80. And the square root of 80, again, we can use Wolfram Alpha, and it would tell us that is 4 square root of 5. And that would be our answer. And that's all that we're looking for here. So we can do it a few more times here. So I'm going to do it at least 2 more. So if we wanted to solve for this one here, the geometric mean of 12 and 27, Well, x would equal the square root of 12 times 27. And again, we can just type this into the calculator. So if we type it into the calculator, 12 times 27 to the 0.5, because if we do this in Wolfram Alpha, we can do it to the 0.5. And if we type this in here, we type the square root of 12 times 27 into the calculator, we would get 18. So it's not going to always work out that we have radical answers. We can get whole number answers, like this one here. We ended up getting 18. And that's it. That's all we have to do for this here. So I'll look at this last one here, 18 and 54. And again, if we're using this here, the geometric mean is equal to the square root of a times b, which here would be 18 times 54. And at this point here, we just have to plug this into the calculator. So 18 times 54. And if we do this in Wolfram Alpha, we'll put it to the 0.5, which is the same as taking the square root. And if we do that, we'll get 18 square root of 3. And that'd be our answer. And that's all we're going to do here for today. So we have those two triangle setups and this here. If you have any other questions or any questions about any of this here, please let me know.